we're here on the edge of the land and the sea, on the boundary in Southampton Docks, which is a very exciting place to be, very noisy behind us. But this edge between the land and the sea is very relevant to the work that you do. So tell me about that.
Yeah, exactly. My work is on satellite altimetry. And this gives us the opportunity to show you what we are trying to measure with satellite altimetry. Because if we look at this very dock in front of us, we see a sea surface, and one of the things that we measure from space up there is the sea level. But we also see quite a lot of little wavelets at the surface of the sea. These are related to wind, to the wind that is blowing here. It's an almost immediate response of the sea surface to wind that everyone can experience. When you look at a pool of water and there's a gust of wind, you will immediately see the surface of the water to become full of little wavelets, and we can use those as a measure of the wind. We see it from space. And also there's not much of a wave field, or a wind wave field here at the moment, because we are in an enclosed basin, but we can measure that one as well from altimetry from space. Now, I've been working in recent times on developing the field of coastal altimetry, which means pushing traditional satellite altimetry closer to the coast. Satellite altimetry has been for many years, at least 2.5 decades, the workhorse of operational oceanography, a very powerful technique. You see lots of things in great detail, and is being used, and it is used over the open ocean to look at the ocean dynamics, eddies and currents, the signature of the big currents across the ocean. And it is fed into the models that oceanographers use to predict currents, and it is useful also for weather prediction. Now, traditionally, this would not work at the coast. What do I mean by the coast? So let's say that the last 10 miles, 10 to 15 kilometers, for a number of technical reasons, it is more difficult to extract reliable data from altimetry in the coast. When the satellite up there starts seeing the coast in its footprint, which is a few kilometers across, things get corrupted. Rather, echoes that we have to process in order to extract the signal gets corrupted, and we need to be particularly clever in the way we reprocess them to extract meaningful information. That's exactly what I've been doing in the last few years.
So when we think about looking at the globe as a whole, lots of it is just big patches of open ocean, miles and miles from land, and things are relatively simple there. But as soon as you start getting closer to land, which is the interesting bit, then it gets difficult, and that's the focus of what you're doing. It
is the interesting bit, because remember, the coastline is the interface between our society and the sea, and any changes, like changes due to global climate change, will impact the society mainly by what happens at the coast. So take sea level, for instance. We've been measuring the rise in sea level for many years using tide gauges, and tide gauges are at the sea. And we've been using altimetry very successfully to measure the rate of sea level over the open ocean. We've got beautiful maps showing how it changes from region to region and basin to basin, and people are trying to find the fingerprints of the various processes contributing to that in those maps. But we've got the measure over the open ocean from altimetry, we've got the measure from the tide gauge at the coast. There's a gap in between, which no one has filled. We are not expecting those measurements to be much different on a global scale, but regionally there might be differences due to the local conditions, for instance. And no one has filled that gap as yet. One of the aims of coastal altimetry is to recover the data that will allow you to fill that gap.
And what is it in that gap between the open ocean and the coast, the land? What data do you want? What do you want to know?
Well, we measure three things. The first one, as I was mentioning, is sea level. And sea level is, well, first of all, linked to the ocean dynamics, but it's also, when you look at it over a long period, is a formidable indicator of climate change. Sea level is one of the essential climate variables that we want to measure to see where our planet is going. The other thing that we measure is the significant wave height field, so the wave field, and the third thing is the wind. And all these three things are poorly characterized in the coastal zone. But with altimetry we can get to know more about that.
And so what sort of things do you do? As you can see, if you imagine a satellite footprint as a sort of circle moving maybe from the ocean onto the land, what sort of problems do you start to get to as you get to land, and what can you do about it?
Well, let's say that the way that we estimate those quantities over the open ocean is to look at the signal bouncing back to the satellite from the surface of the sea and interpreting that signal, which means fitting that signal with a mathematical model that we know describes the various phenomena. When you get closer to the coast, you start seeing a lot of weird things in your footprint. Some land or little islands may enter the footprint. Also, there might be patches of very calm water like this dock that we've got here, and this will give a very bright return. For the satellite, it's like looking in a perfectly flat mirror. It will get big spikes of signal back, and this spoils the algorithms that we're using over the open ocean to recover the signal. We need to devise new, better algorithms that are specific for the coastal zone and account for all these phenomena that I will say here.
So you used to throw that information away, but now you can actually make use of it.
But now, yes, there's this new field of coastal altimetry that colleagues around the world have been working on for a few years. It's a nice, lively community devising all the little techniques that will improve the data, and bit by bit we are recovering more and better data in the coastal environment, and starting to link the open ocean measurements with those at the coast.
And what sort of things can that data be used for? Once you know the significant wave height or the winds in the coast, what's that useful for?
Let's take the significant wave height, for instance. One of the things that you want to study when you get to the coast is how the shape of the coastal morphology will create changes in the wave field, so sheltering effects, for instance. This is important for any coastal manager, having, for instance, to design defenses or account for the sediment transport or how the wave field changes the coastal environment. Another thing that you want to see is the shoaling of the waves as the water gets shallower and shallower in some places. And we believe we can now start to measure all this with the satellite altimetry.
So this is all very useful day-to-day data, and one of the places where people think most, I think most people, even if they live on the coast, they don't think very much about what the sea's doing, but when it comes to them, then they want to know about it, and big storms can push water onshore. Tell me a little bit about storm surges.
Yes, storm surges are one of the deadliest natural phenomena, and unfortunately storm surges in the past, even in the recent past, have resulted in huge loss of life and huge damage to property. There's a lot of people around the world trying to predict storm surges, and in order to predict them you need to input the data about what the weather is doing, what is the state of the ocean, into models. Now, these models, of course, need to be accurate if you want to make an accurate prediction. Coastal altimetry can be quite useful to refine your models, because we can look at the storm surges of the past, and when there is an altimeter overpass over one of these surges, you get a very unique measurement of how the water piles up from offshore into the shore, and that kind of measurement you can't get with any other technique. Now, you can then feed that measurement into your models or compare that measurement with the output of your models and see which models are doing well and which models are doing not so well, how you can see how to improve them and in the end improve the predictions.
Let's just go back to the concept of a storm surge. So when there's a storm out on the ocean, you'd think it wouldn't bother humans very much, but actually that will push water towards the land, and if the tides are also high at the same time, the ocean comes over the land.
Exactly, and that's the result of two effects, in fact. The first effect is simply due to the variation in atmospheric pressure. When you've got a big storm, there's normally a low in atmospheric pressure. What happens, in simple words, is that the sea is sucked up by the atmosphere. You've got this drop in atmospheric pressure, the sea level goes up. Roughly speaking, it's just an approximation, but just as a rule of thumb, for any millibar of drop in atmospheric pressure, the sea level goes up by 1 centimeter. Now, with a big storm, you might well have a 60-70 millibar drop in atmospheric pressure with respect to normal conditions. So that means already 60-70 centimeters of sea level going up.
So those are the numbers we see on weather maps, where it's about 1,000 normally, and it gets a bit above 1,000 or a bit below if there's a really big storm. And so you can actually see from a weather map, you know, approximately what that extra contribution might be. If the atmosphere isn't pushing down on the ocean, the water will come up a little bit.
It will come up, yes. Of course, this kind of response gets a little bit more complicated when you've got complex topography and then when water cannot move that freely. But the idea is that, you know, the lower the pressure, the higher the sea level goes up. And then, of course, there's the local effects of winds that might well push and pile up water in a bay. For instance, with a hurricane, you know, where the hurricane is pushing, on the side of the hurricane where the winds are going towards the coast, you will have an accumulation of water towards the coast, which is, for instance, what caused all the floods for the Katrina hurricane back in 2005 in the United States, in New Orleans.
And so these are data that you can measure from satellites, because it's changed in sea surface height, which you get from altimetry, and then the wind data, you were just talking about that, getting that from the coastal altimetry. So the things that allow you to forecast how big a storm surge might be, that data, a significant part of it comes from satellite measurements.
Yes, of course, because satellites are really what gives us the global view of those phenomena that otherwise you couldn't get with any other techniques.